So in this last section, once again, the numbering may not line up. I think in your homework, it might be called 4.4. And this is kind of also part of 4.3, so it doesn't quite line up perfectly with your homework, but we're going to go over the multiplication rule, complement, and conditional probability. So it says that if you guys remember from the previous section, we had our, you know what, I'll use black this time. We had probability of A and B was equal to the probability of A times the probability of B, given that A already occurred. So I did in the last video, I solved for the probability of B given A. So I divide both sides by A, divide both sides by probability of A, and we end up with the probability of B given A, right? So this guy is equal to this, which is the probability of A and B divided by the probability of A. And, you know, just something to keep in mind, whatever the given is, that's what you divide by on the other side, okay? And then they just gave you these formulas. You could memorize them or just know where they came from. Either way works. And notice the converse is not true. The probability of B given A is not the same as the probability of A given B. That does not mean the same thing, okay? So this problem, it says, on New Year's Eve, the probability of a person driving while intoxicated is 0.32. The probability of a person having a driving accident is 0.09, and the probability of a person having a driving accident and being intoxicated is 0.06. What is the probability, given a person selected at random has had a driving accident, that they are intoxicated? So what I'm going to do is I'm going to do probability and I'm going to write down what they said. What is the probability given a person selected at random has had a driving accident? So we know given they had an accident, right? That they are intoxicated. So I'll put I for intoxicated, okay? So the probability of the fact that they're intoxicated, given that you already know they've been in an accident. Well, we know that's going to be the probability of accident and, intoxicated divided by, and remember, the given is always what you divide by, so probability of accident. So I come over here and I know the probability of getting in an accident. Let's see here, the probability of person driving while intoxicated. So the probability of being intoxicated and a person driving while intoxicated is 0.32. The probability of a person having a driving accident is 0.09. And the probability of a person having a driving accident and being intoxicated is 0.06. So that's this one right here. Okay, so I'm going to do 0.06. And then what's the probability that they have an accident? The probability of a person having a driving accident is 0.09. So all I'm doing, you guys, is I'm just reading the statement and I'm finding the probability, and it says driving accident and being intoxicated is 0.06. So I put that here. Then it says the probability of a person having a driving accident is 0.09. So I put that there. I put that there. So then when I plug this into my calculator, I get 0.667 if I round off. And that is my probability, given that I know this person's already been in an accident, that they are in fact intoxicated. And I'm just using the formulas above. That's all I'm doing, okay? So let's use a table now. It says below in the table for the results of the polygraph test, find the probability the subject had a positive test given the subject lied, okay? So let's see here, probability the subject had a positive test result. So I'm gonna put plus and negative, so plus for positive test result, negative for negative result, and I'm gonna use L for lying, and then you know, a little bar over L for not lying. Or you know what, I'll put T for truth, okay? Because if they're not lying, they're telling the truth. Okay, so it says find the probability the subject had a positive test result. So positive test result given that the subject lied. Okay, so we're finding the probability of a positive test result given they lied. Okay, so that means that we're going to have to do probability of lying and positive test result divided by the given, which is probability of lying. Okay. So again, I'm just using these formulas up here, you guys. Okay. So let's see the probability of lying and a positive test result. Okay. So remember for an and statement, I told you guys the best way to do it is to draw a line with the two categories. So lying. So let's see, subject lied. So that's like that, right? And then positive test result. Positive test. Where did we cross? We crossed right here. So that's 42. So that would be 42. And technically it's 42 out of, I believe if you add all these up, you get 98 divided by, now what's the probability that they lied? Well, we just have to add up everybody that lied. So everybody that lied is 51. So we're going to say 51 out of 98. So this is going to become 42 out of 98 divided by, but dividing is the same as multiplying by the reciprocal, 98 over 51. These cancel, and that's going to happen all the time. So what some students do is they just start off writing 42 over 51. That's okay. And then we end up with 42 over 51. And then what's that as a decimal? That's 0.8235. So I'm going to say approximately 0.824. That's my probability, okay, about 0.824. All right, so that's the probability that they had a positive test result given that they lied. Well, a positive test result is saying that they lied, and we already know this person lied. So that means a lie detector test caught them, basically, right? That it said correctly that they were lying when they were in fact lying. That's what it's supposed to do. If we know the subject had a negative test, what is the probability that the subject lied? So probability they lied given that they had a negative test result. Okay, so that's going to be probability of negative test result and lied divided by the given, which is negative test result. Okay, so now we got to do the same thing I did last time. We take our little drawing and we do negative and lying. So here's negative and here's lying. So right here at the 9, I think that was, yeah, that was a 9. So I'm going to do 9 out of, and then negative test result out of 41. And again, it's technically 9 out of 9 over 98 and 41 over 98, but the 98s are going to always cancel in this particular problem. So we end up with 9 over 41, which is 0.2195. So about 0.220. Okay. So that is our probability of lying given that we know they had a negative test result. So it's saying that there's a probability or a 22% chance that this person lied given that we know they already had a negative test result. So they're kind of fooling the machine, right? Somebody that lied but tested negative, meaning not lying, they're fooling the machine. So being the subject told the truth, what is the probability the test will be accurate? So let's see, being that the subject told the truth. So we're going to say probability of truth, probability given that they told the truth. What is the probability the test will be accurate? Now you got to understand, if they told the truth, that means they should test negative, right? They should test negative for not lying. So we're going to say test negative. So let's see here. We have to do probability of truth and negative test result divided by probability of truth. So probability of truth and negative test result. Let's do our little line again, our cross. So truth and negative test result. Right here at 32. So 32 out of. Now what's the probability that the subjects told the truth? How many people told the truth? 47. Okay, so 32 divided by 47 would be 0.681 approximately, 0.681. So that would be my probability. And again, I'm always writing down. You guys notice I always write the given first and then I work from there. Okay. Are the test results and actual lying telling the truth independent or dependent? Show using probabilities. Well, let's see here. If they were independent events, then that means that probability of, let's do this, probability of negative test result given they told the truth equals 0.681. That's from above, right? That should equal the probability of negative test result, right? Because if events are independent, then it should not matter if they told the truth or not, right? It should not matter if they told the truth because a given should not matter. So what I'm going to do is I'm going to say, what's the probability of a negative test result? Negative test result would be 41 out of 98. 41 divided by 98, and we get 0.418-ish, which is obviously not equal. This does not equal that. So we know that we don't have a we don't have independent events, because if they were independent, that means that the probability of truth and lying, or a negative test result, which equals probability of truth times probability of negative given truth already happened, should equal probability of truth times probability of negative test result. Okay, remember, if two things are independent, that means that the first draw should not affect the outcome of the second, or one event should not affect the outcome of the second event. But this is a lie detector test. If you lie, it should definitely affect whether you test positive or negative, right? So that makes sense that these values, the probability of testing negative versus the probability of testing negative given that you told the truth, should be different numbers because one does affect the other. So these are definitely dependent. One event affects the outcome of the other, absolutely. Okay. All right, so let's look at this Venn diagram. Okay. So basically, I'll do it in an example. This will be a little bit better in an example than going through all that. So it says musical styles other than rock and pop are becoming more popular. So a survey of college students finds 40% like country music and 30% like gospel music and 10% like both. Make a Venn diagram and answer the following questions. Okay, so let me turn my page in my notes real quick. Okay, so in the Venn diagram, we basically are going to fill in some probabilities that we know. So let's call this event, I guess, event A, and let's call this event B. And let's say that 40%. College students finds 40%. Let's say that this is country music is A and gospel music is B. Okay, and you could use C and G if you wanted to use C for country and B for gospel music, but I already have my notes written out with A's and B's, so I'm just going to kind of keep it as that. Okay, so event A is country, they like country music. Event B is they like gospel music. Okay, and the 10% like both. So here's the thing, we already know right here this has to be 10%. Now here's the common mistake. Somebody will then come and put 40% there, and then somebody will put 30% there, because 30% like gospel and 40% like country. But if you add this section up right here plus this section here, wouldn't you get 0.50? And there's not 50% of people that like country according to this. So what we have to do is we have to take into account that there is this middle portion plus this outer portion. Okay, now let's see. If I add 30% and 10%, that would give me 40%, which is what it says. If I do 10% and 20%, that would give me 30%, which is what it says. Okay, so this is how you have to be careful when you're setting up your Venn diagram. You have to make sure that this end part, you don't count it twice. You don't count it as part of the 30, and then you count it again as the inner part. Okay, so it says, what is the probability of college students? Okay. And remember, there's this out here as well. We have this space out here that does not account for people that like country or gospel, or like country or gospel at all. So what is the probability of college students that like country but not gospel music? So let's write this as a in our notation. Probability that they like country, so that's probability of A, and not gospel, right? So it says not gospel. So that would be B complement, right? The not B, right? Event B not occurring, okay? So if we look at the Venn diagram, well, how many people like probably like country music but not gospel? So remember, this are people that like country music and they like gospel as well. So we only want the people that like country music and not gospel. So that has to be this group over here in the Venn diagram. Okay, so we're talking about this here. All right. Okay, so that means it's going to be 0.30. Okay, so we have that probability. So we can use the picture to kind of save us a little bit of time in terms of work. All right, so then it says, what is the probability that a student likes gospel music given he or she likes country? Okay, so that's a little bit different one now. Probability that a student likes gospel music. So probability of B given that they like country. Okay, so you're saying they already like country. You already know this. What's the chance that this person that likes country also likes gospel music? Well, remember our formula. Our formula from up top says probability of A and B divided by the probability of A. Well, that will end up being, let's see, probability of A and B we know is 0.10, right? Because that's this middle section, divided by the probability of just A. So just A, or I'm sorry, not just A, but overall, all the probability of A, that would be 0.40, okay? So then we get 0.25. So that would be our probability that a student likes gospel music, given that you know ahead of time that they already have said they like country, okay? So that's conditional probability once again. It says, what is the probability of college students liking neither country nor gospel? So probability of liking neither country and gospel, okay? Well, we know that based on the Venn diagram, isn't that all this out here? These are people that don't like anything. Well, what's the total probability inside? We got 0.3, we got 0.1, we got 0.20. So that adds up to 0.6. So we're just going to do 1 minus 0.60, and that should be 0.40. So I'm going to use my idea of total probability and the complement to get 0.40 or 40%. Okay, so this is how you can use a Venn diagram to kind of save you from writing out work sometimes. Okay, let's take a look at another one. Now, pause the video and you guys try to set this one up. Try to see if you can do this one without me just telling you how to do it, okay? All right, so you guys should be back from your pause. Hopefully you guys gave it a shot. So your labeling should have gone like this, 0.12, 0.15, 0.1. And let's read where all this comes from. You have applied for 2 scholarships, a merit scholarship, M. Okay, so this is our merit scholarship, right? And this and an athletic scholarship. Assume the probability that you receive the athletic scholarship is 0.25. The probability you receive both scholarships is 0.15, and the probability of getting either athletic or merit is 0.37, or both is 0.37. Fill in the probabilities in the Venn diagram below and clearly label each area, blah, 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 blah. Okay, so they already gave us that. So we know that 0.37 is the probability of getting either athletic or merit scholarship or both. Okay, so let me see here. I feel like something's missing here. Oh, I see. Okay, so this is, they're trying to throw us off a little bit. So it says, assume the probabilities that receive an athletic scholarship are 0.25. So you know that the whole thing is 0.25. But then it says for an athletic scholarship, it says the probability you receive both scholarships is 0.15. So the fact that I know this inner chunk right here has to be 0.15, and then when you add everything up, it has to be 0.25. I do 0.25 minus, I'm sorry. Yeah, I do 0.25 minus 0.15, and that leaves me with 0.1. That's the leftovers. That's what's left over for just an athletic scholarship and not both, not getting also the merit. Now that means that this section combined is 0.25. So what's the leftovers if we get 0.37, right? Well, the whole thing, all the circles combined have to add up to 0.37. But I already have 0.25 here, right? I already have 0.25 for that section. That means that this little section here has to be the leftovers to get to 0.37. So then that's where I got my 0.12 at, okay? So 0.12, 0.15, and 0.1, all right? So, and again, Venn diagrams, don't let the surface area of the circles sway you. It's just two representations. So technically this is 0.15 and it looks smaller than 0.12. I'm sorry, it looks bigger than 0.12. So don't think of it that way. Just think of it as the and area, the overlap is 0.15. That's what's important, okay? So it says, what is the probability you receive a merit scholarship? Okay, well, that's gonna be probability of a merit scholarship. Just a merit scholarship. They didn't say just merit and not the other. They said in general, what's probably get a merit scholarship? Well, that's going to be this whole area here, because all of these individuals get a merit scholarship, okay? So all of those individuals get a merit scholarship. So that's going to be 0.27, okay? Now it says the probability you do not receive either of the two scholarships. So that means you're not going to get this and you're not going to get this. Well, we know the whole thing is 0.37. So then what's out here has to be 0.63. Those are the people that don't get either. So probably, or you that, you know, you're not going to get either, the probability of that. So you're going to say probability of merit not and athletic not. So that would be 0.63. Oh no, yeah, 0.63, because 0.63 and 0.37. Well, basically I'm just doing 1 minus 0.37, which is 0.63. Okay, so I'm just basing that off of this writing right here where it says the probability you get an athletic or a merit or both. Okay, so we get 0.63. So hopefully that kind of helps you guys with this example and this example, work with any Venn diagrams you may see using probabilities. Okay, so now we're going to do, let me see here. This would be contingency tables. If you're asked to determine whether two events are independent, here are your options to show independence. You just need to test one. So you just show that that's what I did in the previous example. The probability of B given A is still the same as the probability of B without ever A occurring. That means that A did not affect B, right? But if it does change, if they're not equal, then that means A did affect B. Okay, so let's go through and kind of work with this real quick. It says probability that a married adult is very happy. So let's do probability very happy. Okay, so very happy is right here, and that would be 370 divided by, did they tell us how many? 603, right? So when we do this in our calculator, we should get approximately 0.614. Okay, I normally use 3 decimals in general. Okay, so what is the probability that a married adult is very happy given they are male? So probability of very happy given they are male. So what we're going to do is our formula again, probability of male and very happy divided by probability of male. Okay, so male and very happy. So we go like this and we go like this, and that's 221 divided by probability of male. Let me see here. Male is 325. So whatever this becomes, I think this is 0.68. Let's do 221 divided by 325. Yep, 0.68. Okay, so far so good. What is the probability that a married adult is very happy given that they are female? So probability that a married adult given that they are female. So given female, very happy. That's going to be probability of female and very happy divided by probability of female. So let's do the same thing we did last time. Female and very happy. Where did we cross? 149. Divided by probability of female, 278 over 603, but the 603s are going to cancel once again. So 149 over 278 is approximately 0.536. Let me do this on my calculator just to be sure. 149 divided by 278, 0.5359, so about 0.536. Yep. So it says, does happiness depend on gender? Then are these events dependent or independent? So it does seem to depend on gender because probability of, so they said, oops, let's say that you want to show very happy, right? So probability of very happy, how do I say this? Probability of very happy given male should equal the probability of very happy if they are independent, right? So let's see, probability of very happy given male is 0.68. Probability of just being very happy would be what? Very happy would be 370 out of 603. All I did was I took 370 and I'm going to divide it by 603. Oops, we already know this one. Sorry about that. That's right here. That's 0.614. Right? That's this one right here. So all I did is I said, if in fact they were independent events, the probability of being very happy should be the exact same as the probability of being very happy given your male and the probability of being very happy given your female. It should not matter, right? If they were independent. But because these are not equal, that tells me, this tells me they are dependent events, right? So this means that yes, happiness depends on gender. It does appear so because whether you're male or female basically changes the probability of if you're happy or not. Okay, so that's one way you can do it. There's other ways, but that I'm just using one of the ways that we can check, right? It says that right here. Okay. All right, so this will be the last section. I believe this is part of 4.4 in your notes. I don't think it's called 4.5. I think they just all put it together. So this is the counting. It says, in this section, we will cover methods for counting the number of possible outcomes in a variety of situations. So the fundamental counting rule for a sequence of two events in which the first event can occur m ways and the second event can occur n ways, the events together can occur m by n ways, or m times n, okay? So it says if someone uses a combination lock to lock his or his bike to the rack and it has a 5-digit code, how many different combinations of numbers are there to choose from? Possible digits are from 0 to 9. Okay, so let me turn the page of my notes. Okay, so here we go. So we know that combination, like possible digits are 0 to 9, 5-digit code. So there are 10 for the first one. Oops. 10 possibilities for the first one. The next number, there's 10 possibilities. 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 So this is actually 10 to the 5th, which is equal to 100,000. Okay. So that's how many possibilities we could have. That's how many possibilities you can come up with a 5-digit code when you're going from 0 to 9. Okay. Let's see here. That's all the different combinations we can make. Now, just a quick note, the factorial symbol is this little symbol like this. So if I say 12 factorial, what that really means is 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what 12 factorial means, okay? So we're going to use our calculator for this. So what I'm going to do is I'm going to go to my calculator and I'm going to go 12, and then I'm going to go into math and go to probability. And right here, there's that factorial symbol. We hit enter and it tells us it's that huge massive number. What is that? 479 million. 479 million 1,600. So 479 million 1,600. That's what 12 factorial means. Okay. So you do 12 times 11 times 10 times 9 times 8, and the numbers just get bigger and bigger and bigger and bigger and bigger. Okay. So now, suppose there are 5 people, Jessica, Chris, Vanessa, Mike, and Eric. How many ways can they stand in line? So this can be rewritten as 5 factorial. Okay, because they could have 5 times 4 times 3 times 2 times 1 possibilities. Okay, so this would be 120. Okay, so factorials come into play a lot in statistics, and also when you're trying to find different ways that you can rearrange things and how many different possible outcomes there could be. So not just statistics, but finding outcomes or sample size or number of elements or number of different ways something can be arranged. Okay, so here's the permutation rule. When all items are different, okay, so when all items are different, there is n different items available. We select R of the n items, okay, and then we consider rearrangement of the same items to be different. So ABC is different from CBA. Even though they're both using the same letters, it's 2 different things, okay? So those count twice, all right, instead of just once. So permutations, order, so put this in your notes, order matters. Okay, over here for combinations, when we get to combinations, order does not matter. Okay, so when we get into permutations, or I'm sorry, for combinations, order does not matter. All right, so let's focus on this one real quick. This video is already getting longer than I thought. I thought it was going to be faster than this. Okay, so here's this formula. I am not in general going to make you guys do this formula. I'll show you how to do it first by hand, and then we'll do it on the calculator, okay? So it says in horse racing, an exacta is won by correctly selecting the horses that finish first and second in correct order. If the bettor randomly selects 2 of the horses out of a field of 20 horses, what is the probability of winning? So what this means is, okay, in this particular problem, our N is 20 and our R is how many we're choosing, okay? So we're gonna do 20, choose 2, choose 2. So that's how you write it, NPR. N equals 20 horses and R is how many we're choosing, which is 2, okay? So when you write this, I'm gonna write this formula, 20 factorial divided by 20 minus 2 factorial, okay? So this will become 20 times 19 times 18 times 17, all the way down to times, to 1, right? Divided by 18 factorial, which would be 18 times 17 times 16 times 15, all the way down to 1. But if you notice, I can cancel this whole tail with that whole bit because they both have 18, 17, 16, 15, so on and so on. So what I'm left with is 20 times 19, which is 380. Okay, so if they say if a bettor randomly selects 2 of the horses out of a field of 20, what is the probability of winning? The probability of winning, well, there are 380 possibilities, so it would be 1 out of 380. Okay, so this would be our probability. All right, so in this case, it says the horses finish first and second in correct order. So that means if you wanted to pick Shadow to be first place and Celeste to be second, it has to be in that order for you to win. If you pick Celeste first and Shadow second, and it turns out in the actual race that Shadow's first, then you lose. It doesn't count. So you have to not only pick the first and second place horse, but you also have to pick the first and second place horse in order, the correct order. So that's why order matters. Now we come over here. Oops, let me show you how to do it on the calculator now. So on the calculator, what I'm going to do is I'm going to do 20, and then I'm going to go math, and I'm going to go back over to probability, and there's NPR right there. And I'm going to choose 2 and hit enter. And I get 380, just like we thought, okay? So hopefully you guys understand you don't have to do that formula. I'm going to let you use the calculator to do it. All right, so let's go back to our notes. So let's try this next one now. So this next permutation rule, when some of the items are identical to others, this happens when they talk about like words like Mississippi or, you know, just words that repeat a lot of the letters, and they say how many different ways could you rearrange the letters. So this is probably when you have to work with something like this. So it says, how many ways can A, B, B, C, C, D, E be arranged, okay? So we consider rearrangements of distinct items to be different sequences, okay? However, when some of the items are the same, you can't really distinguish. So what we're going to do is we're going to say, okay, for this problem, it's n factorial first, okay? So we have to count up how many we have total in this particular problem. So n equals 10, right? Because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we can do this. We can do 10 factorial divided by, now what these little ones are right here, these little ones here right are for the repeated letters, okay? So how many times is A repeated? It's repeated 4 times. So we're going to say 4 factorial, right? How many times is B repeated? It's repeated twice. So we're going to say 2 factorial. C is repeated 2 times, so 2 factorial. Now D is 1 factorial, but you don't even have to write it because D is 1 factorial is just 1, and E is 1 factorial. So what we end up with is 10 factorial divided by 4 times 2, and 4 factorial is just 4 times 3 times 2 times 1 times 2 times 1 times 2 times 1, okay? So what I'm going to do is I'm just going to take out my calculator, and I'm going to do 10 math factorial, enter, divided by, and then I'm going to do parentheses, 4 times 3. I don't want to even waste my time writing out the factorials, but I could, times 2 times 2 times 2. And I get 37,800, okay? So we come back over here, and this is 37,800. Okay, so it says how many ways can these letters be rearranged, and we find out that it can be rearranged 37,800 ways. Okay, so now the combination rule is the same as the other one, but we have this little extra times r factorial. So with the combination rule, ABC is the same as CBA. There is no difference between the two of them, okay? So you can't count that as 2 separate rearrangements. That's just one. So if I said, what about ABC and CBA and BCA? All of these are actually the same, right? There is no difference between them. Those would all count as one rearrangement, not as 3. But if we were doing permutations, they would count as 3. So permutations normally have more outcomes, more possibilities, okay? So now we're going to do the horse racing one. Something called a canella is won by correctly selecting the horses that finish first and second, where the order doesn't matter. So as long as you pick Shadow and Celeste, it doesn't matter who comes in first and who comes in second. They both count, okay? If the bettor randomly selects 2 of the horses out of a field of 20, what is the probability of winning? So I'm going to do the same exact problem. I'm going to do 20, choose 2, but I'm going to use NCR, which is a combination, because it doesn't matter which horse comes in first and which horse comes in second. We count that as the same. So that's the same winning ticket, whether it's Shadow first and Celeste second or Celeste first and Shadow second. It doesn't matter. We win with either one. Okay. So what I'm going to do is I'm going to do 20 factorial divided by 18 factorial times R, but R was 2 factorial. So instead of doing all of this, I'm going to once again get out my calculator, and I'm going to do 20 math factorial. And I could have done it probably faster by hand, to be honest with you. Divided by parentheses 18 factorial, times 2 factorial, which is just 2. And we get 190, which is half of the 380 from the last one because of this extra 2 factorial. So this is 190, okay? So all you have to do is type this in your calculator. But if you wanted to do it the hard way, or not the hard way, but by hand, you could do 20 times 19 times 18 times 17, so on and so on, all the way down to 1, divided by 18 times 17 times 16, all the way down to 1, and then times 2 again. And what you would notice is that all of this would cancel with all of this, and then 20, oops, not that, all of this would cancel with all of that, right? That would just become 1 and 1. And then this 2 would cancel with this 20 and become 10. And then we would be left with 190. So 190 possible ways. But they want to know the probability. So the probability of winning, that's just the number of outcomes. That's just the number of ways. Probability of winning equals 1 out of 190. Your one ticket, okay? So remember, here's how you can find these on your calculator, NPR and NCR, so you guys don't have to do all this by hand. But that's going to do it for this video. Sorry, I didn't mean for this one to be so long. I thought it was going to be quicker, but there was more than I thought. Thanks for watching, guys. See you in the next meeting.